Yeah, I'm excited to talk about some of our recent results on sort of learning in sort of quantum experiments. And it's going to tell you a bit how it relates to linear algebra uh, towards the end of the talk. But I think it's kind of an interesting area that's gotten me really excited about potential applications for quantum computers that I hadn't thought so much about in the past. And it really kind of energized my belief that they're going to teach us something about the universe that would have been very, very hard to learn without them. And I think it's some of this work, kind of along the series of papers that I'm going to talk about, has really even changed my perspective a bit philosophically on the way that we do science, but I won't expect that to come across in such a short talk. So yeah, I want to talk a little bit about quantum machine learning and data advantage. And you might think at a glance when you see the words quantum machine learning put together, kind of like, wonder what this is. Are they just smashing buzzwords together for maximum effect? And I hope to convince you maybe that's not the case, that there's some interesting meat here that can be had that we can learn about from this setting as opposed to a more general computational setting. And so often when we talk about quantum computers, we talk about what I would call computationally limited problems, meaning we have some simple input. I want to give it to you, and I have some expectation of the task that I want to perform. And given that input, there is some known computational procedure, even if it takes a really, really long time to get to the output. And an example of this might be, say, I want to factor products of large primes, or I have some Hamiltonian with a small specification that I'd like to output. And the hope is that for many tasks, a classical computer might take something like an exponential amount of time, while a quantum computer might have some very nice low polynomial scaling, maybe even linear if I'm super lucky. But I want to kind of contrast this to a slightly different type of problem that you might call data limited problems. And what I mean by this is that for this type of problem, I start collecting data about some problem that I'm interested in. And if I don't get enough of that data, then simply put, no computation is possible to overcome that. So these, if I'm getting in information from a state, so this is the setting that I'm in, maybe I'm collecting measurements for my environment, and those measurements have some amount of noise, or I transduce some small amount of quantum data into my device, but it comes at a very slow rate, and I can only get so many measurements done, here where I'm calling that a limited number of copies of my quantum state. And in some cases, say if I just process this classically, and this will be kind of the subject of most of this talk, then I need an exponential number of copies for some tasks, whereas a quantum device with a very limited memory capacity might only need a handful of these copies. And this is kind of an interesting setting, especially for near-term and non-error corrected devices, because in this setting, no amount of computation that my classical adversary does could actually overcome this in a setting where data is very, very limited. And I'll get to more what I mean by copies of a quantum state. Given this, I often get the question when I say copies of a quantum state, what about this no cloning theorem? And what I'll mean is that I get some source of data that's producing these states, and I can collect one and keep it. And then that source might produce another one, and I could also collect it and keep it. And some of this was motivated by recent work where we did, there's kind of this intermediate class of problems that's especially applicable to machine learning, which is there is some problem I'm interested in. It has a known computational procedure, but the complexity actually formally changes once I have just a small amount of data. And this kind of helps me to conceptualize why I might be interested in these data limited problems, where now the problem very much depends on collecting enough data. So what's a motivating example for this type of data assisted problem, so you can kind of see at least what I'm talking about? So imagine I'm given some quantum circuit. I'm just going to call it U, Q, and N for some reason. And then I'm going to have some input, and I'm going to encode that input. Say it's just P classical numbers. So I'm just going to put them in and use them as amplitudes once I normalize them in a quantum state. And so I'm going to say that my task is to compute the expectation value of some other operator O on this circuit. So if you don't know too much about quantum circuits, all you need to know is this will be a very long one, and this is something that we should have that will be very hard classically. Because this is an arbitrary length quantum circuit, It's just an arbitrary Hermitian operator. Direct simulation of this has to be at least as hard as BQP. And we think because it's arbitrarily long, I could actually make it much harder than that. But basically, we're going to say clearly this is a very powerful function of x. And now I'm going to change the setting a little bit. So if you imagine the first case, if I give you even a single input, that had to be at least as hard as simulating a quantum circuit. But now I'm going to give you a little bit of data, a little bit of input and output. And if I rearrange how I want to compute that task, then I quickly kind of see that it has this somewhat simple form where I've hidden all of the complexity of these giant operators in the middle into this B. And this B turns out to be kind of small. And so what that means is that given some data, this is interestingly at most a quadratic function with p squared coefficients. So the change here is that with no data, this is an arbitrarily hard quantum circuit. And with actually a very small amount of data, this is an almost trivial learning task. And so this is kind of a toy example. You look at this and you're like, okay, but that was because you used amplitude encoding. That was because you used a very small input space. But this type of thing motivated us to look for a more general class of problems where this might hold. And this was the subject of our paper that I won't talk about in too much detail today, but the power of data in machine learning, which basically meant that with a little bit of data, you actually elevate yourself outside of sort of normal classical algorithms for certain problems where some small sort of data for each individual problem size can make certain quantum problems easy. And we kind of plumb the depths a little bit of what that can look like. And you might be asking, well, do you have an example I might care about, say at the Doing Linear Algebra for Quantum Systems conference? And one that people actually seem to care a lot about, including myself, is the prediction of many body ground states, for example. We spend a lot of time diagonalizing those, coming up with efficient approximations, doing linear algebra in exponential spaces. And it turns out that under some restrictions, a little bit of data in each phase can allow you to efficiently predict these ground states. And so this is an example of a problem where you can accidentally make a potentially difficult problem into an easy one with a bit of data. And so then you start to ask yourself, well, is the fate of quantum computers just to provide training data for classical models so that at some point we've tabulated enough data that we're essentially done for purposes of practical problems? And luckily, some of the same authors went on to say, well, perhaps not. There are cases where you can take data directly from a device and you can process it in a way that no amount of single copy processing could ever compete with this. And so we wanted to build on this and say, well, when can we demonstrate this? When can we break it down to the simplest possible task? And that's sort of what we wanted to do in the work that I'm going to primarily talk about, is compare these two interesting settings about learning from a system. And I'll get more into the specifics of exactly what we're learning. But the setting we want to realize is there is some physical system in the universe that I'm interested in. And this data, it could be another quantum computer doing an interesting computation. It could be some measurement that I do on a different quantum system with a sensor, say like a gravity measurement. And I'm going to collect that in my quantum sensor, and I'm going to compare two settings. In the first setting, I hand you one copy of this state at a time, and you can do anything you want to it. This is kind of meaning you can rotate it, you can apply a quantum circuit to it, you can do an arbitrary POVM, but the rules are that each time you receive a copy, you do this and it sort of destroys the state. And so I'll call this the conventional measurement setting because this is sort of how we do experiments in most cases today. And I'm going to contrast that to the case where if you receive a quantum state, you can now also do any of the things you did before, but you have one extra operation, which is I can store it for a moment in quantum memory. So I take this state and then I leave some of my qubits aside and I allow myself to collect at least one more copy of the state and then do things on multiple of them at once. And so this is the kind of task setting where we're going to get some number of copies of rho in each case. And I want to think about the difference between these two. And I'm going to consider also the additional case where instead of just receiving states, I can now take a state like a quantum sensor, expose it to some external process, get that quantum sensor back, and then now do something else to it. And once again, I'm going to contrast these two settings where I can get my quantum sensor back, do anything, or get it back and kind of leave it for just a moment. And kind of what we do that's in this particular work is we find an exponential advantage in this setting where you can keep at least one copy around on two different tasks. And really kind of our interest in going differently than kind of the last two papers is to kind of break it down into the simplest task possible with many co-authors from those papers, so we can kind of understand the essence of where these separations come from. So what is the simplest task we can have an advantage on? So perhaps one could find one even simpler, but this is going to be a pretty easy one. So what's my setup? So I'm going to take n copies, meaning like I'm going to collect n of these copies of the state row, which I'm just going to say is the identity plus some coefficient times a long poly operator. So P is just some general n-qubit poly operator like Z1, Z2, X, or ZX, or something like this. And I'm going to allow all of my learning agents to know the form of the state. So they know it takes exactly this form, but they're not going to know the exact value of alpha or the exact value of the poly operator. And it's worth noting that this state is actually unentangled, but it's not factorizable. And it can be realized with a depth one Clifford circuit and a little bit of classical randomness. So this is kind of an interesting fact where I'm actually not going to require any quantum entanglement, but what I will have is very large classical correlations across the entire system. So I'm going to contrast again this setting where a copy is given at a time for conventional measurements versus a copy is given and I'm allowed to keep it around for a little while and do some kind of joint entangled measurement on it. And my task will be, you're given each of these copies in these settings. You can take any measurements you want on the n copies. You collect some classical signatures of this state. And then after you've collected all this data, someone now gives you a new poly operator. So you're not allowed to receive any more copies after this point. And you have to tell me the expectation value of this operator, or rather its magnitude. Alternatively, you could be given two candidate operators and be asked to distinguish which one is larger than the other. And so you might ask, after you see the quantum part of this, what was kind of the heavy lift in this work? And actually, the heavy lift is quantifying the best possible conventional experiments. So the quantum algorithm will be, importantly, very simple. And what you can show on the classical side is that the best conventional strategy, meaning receiving one copy at a time, in fact, takes on the order of an exponential number of these measurements with the number of qubits in your system in order to predict this new unknown poly operator with sufficient additive error and high enough probability. And kind of a sketch of what's done. So this is a dramatic simplification, but basically we reduce it to a discrimination task and use these sort of new tools that have been developed for distinguishing even adaptive protocols, where at each level of the experiment, you're allowed to use all previous information, and you kind of reduce it to the task of distinguishing between some totally mixed state and this alternate hypothesis of this target state that you want. And basically, given this particularly simple form of the state and the all possible measurements, you can basically bound the differentiation that's done by any POVM, and it gives you exponentially vanishing returns. And then you can ask, okay, well, no conventional strategy, and that includes arbitrary long quantum circuits on single copies, can distinguish between these two without an exponential number of copies. But what about the quantum enhanced case? And so it turns out, if I take sort of this setup, and this kind of helps you imagine how we're going to do the experiment as well, which is I prepare one copy on half my qubits, and then I do another copy preparation on another half. And then I just do Bell measurements between the two. So I've broken it down here for you, but I've just used a simple symbol up here of just kind of C-naughts and Hadamards. And what this does is creates 2n classical bit sort of signature of this state. So you call it maybe like a Bell sketch of your state. And it turns out that the number of samples you need for this task is independent of the system size, roughly. It's only sort of 1 over this precision that you want, this error that you want in your system. And the computation time for exactly determining this value is basically linear in the number of qubits. So I'll sort of flash for a second that there is sort of a closed form for determining it. It's relatively simple, but you wouldn't know that by the notation I've used here. But that's kind of what I wanted to say about the exact determination. So in summarizing the scales of separation, you've received n copies of this interesting state row, maybe from a quantum sensor. You've taken any measurements you want, you've collected classical signatures, and now I hand you a new operator O, and you tell me its value. And in these two settings, in the conventional setting where I can do even any quantum processing I want, but on single copies, so this is even a more powerful setting than most traditional sensors and processing you'd have, you need at least 2 to the n copies. And in this quantum enhanced setting where I'm using only 2 copies at a time, I only need this sort of 1 over epsilon to the 4th copies. And so you might say, well, this was kind of a contrived problem where you had to work out all the details, like in many quantum settings. And what if could we actually learn from this? So many cases in quantum computing, we need everything to be so perfectly aligned, the phases to cancel in just the right way. Is there any hope of using this kind of strategy to learn things about unknown quantum states where I don't have all the answers? And the question is, say we take these generic kind of 2-copy measurements and we create these sort of 2n bit long sketches of my states, can we use these as quantum features to learn similar things without needing to know the right answer? And this is an interesting question also as we start to use it on a device, because if you compete against the classical learning algorithm as well, perhaps the noise reveals features of the state that would elevate your classical adversary as well. And we're going to look at both the supervised setting, where we're going to kind of teach it how to do this, and actually a little bit later, even an unsupervised setting where that's not actual data, that's a picture off Wikipedia, but it'll show you that we can, in fact, discover interesting features about quantum states. So if I imagine and emulate a quantum data pipeline, so I'm just kind of taking a step back for a second and asking where this fits in the future, given everything we know about quantum computing, noise, quantum error correction. So you can first ask, well, where is this data really going to come from? I've heard that transduction from real quantum sensors is quite hard, and there's a number of places it could. You could be doing a digital quantum simulation somewhere else on your existing device and bring that in. You could have an analog quantum simulation that you're doing in, say, one platform on ions or neutral atoms and perform a transduction to get data into your computational medium. Or it could be something where you actually have this quantum sensor. But in any case, you perform this transduction into the thing that you think you're going to compute on, or your quantum buffer. And then eventually you probably perform a logical encoding so that it can sit around and you can do more advanced processing on it. But importantly or interestingly, this data is essentially always going to be unprotected, at least as far as we know, unless we can encode data. There's going to be some errors in this process. Whereas this right one, we can fit under the more appropriate guise of sort of fault-tolerant quantum computing, where we think if once we get it in there, we can start to do interesting and hard computations that are quite long. And so if this part is sort of always unprotected, then even near-term experiments can sort of tell us something about how robust what I've just said is to real experimental damage or noise. So at some point, we might be able to protect the processing, but if the state preparation and transduction always have these errors, we'd like to know how it's going to work. And this provides a very nice opportunity to actually use existing quantum processors to test some of these things. So that's what we wanted to do. And I'm going to show you first this experiment and then a second one that increases the difficulty considerably. So in this experimental setup, so I've put one of our Sycamore chips as a picture over here. We kind of tile between these system and memory qubits as part of our layout. And the setup we use is that we prepare these states and then pretend we didn't know the circuits which prepared them. This is sort of to emulate the process of collecting data from somewhere, and then we're going to process it. And for this particular experiment, this is a fairly easy thing to do. As I mentioned, this is a constant depth circuit of transduction and preparation, and then we just do some entangling measurements across. But in this setting where I don't know anything about my state, this can still be quite a hard task to learn on. And so what do? We give ourselves exactly what I said, n copies with some unknown and randomly chosen poly operators. I give us some new candidates for each instance of this learning problem. And basically, I want to do what I said before, which is not just write down the right answer, but provide some training data on a small number of qubits, say up to 8 per system. And I'm going to train it on a recurrent neural network so I can go to arbitrary sizes if that's my interest. And then I'm going to actually apply it to larger sizes. So you can see sort of the training loss on the small sizes and how it increases prediction accuracy. And what I compare to here, so I'll take a second to describe the 3 lines, is you can, in the process of the proofs, derive a rigorous classical lower bound that if anyone did arbitrary computation, this is the best on expectation they should do. We then compared that to some data collected from a noiseless classical process to show the gap between true classical performance for real algorithms and theoretical lower bounds. And then we computed on the quantum data that was actually from our real hardware device, going up to a qubit size of 20 per system, so 40 total qubits in the experiment. And you can see that between the classical lower bound and the quantum experiment, there's many orders of magnitude of samples that you'd have to get. And keep in mind that this is a data advantage. So that's why even at 40 qubits, if the amount of data that you collect is limited, there is no amount of supercomputer computation that can be done to close this gap. So we've learned about states, and we did an experiment, but you might have thought it's a little bit unimpressive to do one that's almost unentangled. There's a little bit of Bell measurement in there. But what if we make this process a little more interesting? What if we instead start to talk about processes? So now my task will be given access to some process that I'll just call E n times, determine if that process is either a completely random but time reversal symmetric, so all real entries, or a completely random unitary. And completely random will have a experimental bent to it here, meaning we will just have both a random depth and sort of random assortment of gates on a 2D lattice that will provide some approximation to this. And the setting here turns out is very similar to the setting before, except now it's sort of 2-sided Bell measurements, I guess you could call it. We do a Bell preparation, hand it off to the process, get it back, and do our Bell measurements. So once again, we have these sketches of our state that are 2n bits long. And we're going to lay this out on the Sycamore processor. So this one's a bit more complicated in the sense that you need entanglement within a subsystem. So you need to do scrambling gates on, say, the blue qubits, but then you also need to be able to do joint measurements on the corresponding qubits. So you can imagine there's a lot of swapping and random gate application going on here, and kind of a summary of the experiment that we have to do to get to the depth we're interested in is we're going to do this on 40 qubits with roughly 1,300 or 1,400 gates, and this reaches a circuit depth of about 54 on our current processor. And this part is especially interesting to me because once again, you might say, well, doesn't the stars have to align for you to learn the things you want about a quantum system? If the phases are a little bit off, it's going to be a disaster. And surprisingly, even without putting in training data for this system, we were able to learn something. So let's take this setting again. I'm going to get out my 2n Bell measurements that are a sketch of the state. I'm just going to encode those as, say, I'll take like 1,000 repetitions of that, and I'm going to take the expected value and variance of each of these kind of Bell states. I'm going to make that into a feature vector, encode it into a very basic sort of kernel for similarity, just like a kind of exponential of a sort of Euclidean-like distance between these two feature vectors. And then I'm just going to do PCA. I'm not going to put in any training data. I'm just going to say, explain the difference between any possible states here. And I'm not going to give you any labels, which ones are which. And in the conventional setting, so one copy at a time, you can do this. And basically what you find is just this jumbled mess. So the blue being this general random unitary with complex entries, the red being this other setting with completely real entries. And something surprising happens when you plug in the 2-copy measurements. It basically automatically separates for you. And so to me, this was like a big thing because I imagine collecting data from the universe and I process it. And this is really saying that at least these experiments are going to clue me off to a difference between 2 potentially different physical processes that's utterly invisible without this sort of quantum processing. Granted, this is kind of a contrived setting, but it kind of inspires me that really this is a technology that can show us things that would have been otherwise invisible. And I find that fairly exciting. And this is just sort of kind of a more quantitative quantification of the difference between the two in processes, but I'm going to kind of skip past that in the interest of time. So the final kind of comments and connections I wanted to make is related to one last proof we have in the paper, but have no current means of doing an experiment for, which is we've, in some cases, if you've plumbed the depths on these sort of error mitigation literature, you start to find techniques related to sort of purifying a quantum state, or at least sampling from a purified quantum state. Meaning there are situations in which your error model roughly looks like the following, which is you have a density matrix, which is some amount of uncorrupted data plus some amount of orthogonal errors to that data. And this is not always exactly true, and there are some models in which it's more true than others, but this was the inspiration for techniques like what's called sometimes virtual distillation, where you try to use multiple copies to sample from rho squared. And it turns out that's exactly the same as the destructive swap test or the Bell signatures that we've taken here. And so interestingly, if you use one swap, one destructive swap, you get virtual distillation. If you use the swap as sort of a generator, you can use this as a subroutine to do a quantum PCA, meaning now I can extract this like dominant singular value here, or dominant principal component, which I believe to be my uncorrupted quantum state, or the closest thing I can get to it, given that an unknown state might not have any symmetries I can use in quantum error correction. So in this work, we actually proved that in a conventional scenario, you would need an exponential number of copies to learn about this principal component versus a constant number in the quantum-enhanced setting. So this is yet another case where if I'm processing truly unknown quantum data, this sort of ability to use multiple states, in this case in the context of a linear algebra routine, is sort of exponentially more powerful than if I force myself to think about processing one unknown state at a time. And so the immediate reaction we've often gotten when we said that we proved that quantum PCA has this sort of exponential separation compared to conventional is what about dequantization? So we've heard that many linear algebra routines have been dequantized. What about that? And so we wrote sort of a small auxiliary paper to accompany this one to kind of point out some of the subtleties, especially related to these problems about dequantization. So just to give you a brief recap on what we mean by that. So we often have some quantum linear algebra that we would like to do, like a linear solution of equations or PCA or recommendation systems. And we often lean on this quantum access model some quantum access model in order to achieve such an exponential separation. Otherwise, if you even wrote down the answer, you'd be out of time. And we think about an explicit model where we kind of take all of these classical entries and we encode them into something like a quantum state's amplitudes. Or you can think about a different setting where you have an implicit, say just U, that you act on your system and you read out some amplitudes of a quantum state which are related to this linear algebra problem, or the setting we've been talking about here where someone hands you these truly unknown quantum states. So this is now your potentially accesses to this data. And what the dequantization literature, started by Ewan Tang and many others, is that, well, it's not really a fair comparison to compare directly to stored memory. Really, you should think about these models where you have the ability to probabilistically sample, kind of like in these amplitudes, to query any one of these, because granted you wrote it down, or to simply output the norm of this vector. And if this type of access allows classical algorithms to match roughly the advertised scaling of your quantum algorithms up to a small overhead, we will sometimes call this algorithm dequantized. And so in our context, we wanted to just clarify some of the subtleties of this, which is to say that sometimes it's a little bit too powerful if you apply it in not the right setting. And even in some cases, there are subtleties like the explicit case. So I'm kind of out of time, I think, so I won't go too much into detail of this problem. But basically, even the act of encoding into this quantum access model is a bit lossy, to the extent where for some problems, performing this and then trying to operate on this encoded quantum state requires 2 to the n queries, whereas classical can do this in 1. And that's just because the crux of the problem has been hidden in the precision, and by forcing it into a quantum state, you've done a very awkward thing. And in the other case, if we have these implicit ones, like the case of our quantum PCA, where you're handed unknown states, In fact, having that type of query access immediately allows you to solve sharp p-hard problems, and extracting arbitrary pieces of that state to the precision that would be required for the dequantization can be exponentially costly. So I'm not saying that dequantization is off the table, just that before you have a knee-jerk reaction to, this has been dequantized, you have to think about the setting in which your data is being provided. So just kind of the quick summary and outlook. The punchline I hope people take away is to be excited about quantum technology today, which is to say, if we could find a suitable data source, and I'm not saying we have one now, then even quantum cloud devices today allow us to learn things about these unknown states that could be otherwise inaccessible. And I think that's very, very cool. And in this work, we gave some proofs of advantage of the PCA state learning and process learning, an experimental demonstration showing you that even with noise today and unerror corrected qubits, you could do something interesting. And my hope is that this work inspires new techniques for harnessing quantum data sources, and that it dispels the myth that kind of operating on quantum data, sometimes lumped under quantum sensing, is limited to quadratic speedups. So that's of course true for some specific tasks, but if you generalize the class of tasks that you're interested in, you can sometimes find very interesting ones. And I'm hoping we can find deeper connections to physics and interferometry experiments, and look at other tasks beyond these 2 copy measurements, maybe many copy measurements, and find sort of these simple essence problems where we can learn new things. With that, I'd like to acknowledge all the people that were crucial in this work, especially Robert Wong, Michael Broughton, for getting the experiment and all the hard proofs done, and all of the great collaborators we had on this particular project, which was really a tour de force in bringing proofs and experiment together. And I'd like to thank all of you for listening. Thanks a lot.